You know, in the world of AI, the race has always felt like it's about getting bigger, right? More data, more parameters, just more power. But what if the next big leap forward isn't about being bigger at all, but about being smarter? Today, we're going to dive into a new architectural proposal called Hydra, and it just might be a blueprint for AI models that are not just powerful, but also incredibly efficient.
So here's our game plan. We'll kick things off with the big scaling problem that's facing AI today. Then we'll unpack the 4 key technologies that Hydra uses to try and solve it. We'll see how they all fit together, look at the test results, and then wrap up by exploring what this whole blueprint could mean for the future of AI.
All right, let's start with the core challenge here. The architecture that basically powers everything we know, models like ChatGPT, well, it's called the transformer, and it is starting to hit some very real, very serious limits.
So it raises this fundamental question, right? Why can't we just keep making these models bigger and bigger forever? Well, the answer really comes down to the way they process information.
Okay, so here's the heart of the problem. A standard transformer model uses this thing called an attention mechanism. And what that means is that literally every single word has to look at every other single word in a document to get context. It's powerful, for sure, but it is wildly expensive. The cost grows quadratically. So if you double the length of a document, you don't just double the cost, you quadruple it. That's just not sustainable. What we really need is a model where the cost grows linearly. You double the document, you double the cost. Simple as that.
So how does Hydra even begin to tackle a problem this big? Well, this is what's so clever about it. It doesn't invent one single brand new thing from scratch. Instead, it combines 4 existing, super powerful AI technologies into one single elegant architecture. It's like they've assembled the ultimate high-performance toolkit.
The first tool in the kit, and really the foundation of Hydra's efficiency, is the State Space Model, or SSM. Now, unlike a transformer, an SSM processes a sequence one piece at a time, just carrying information forward as it goes. And the crucial part? Its cost scales linearly with the length of the text. That's the holy grail we were just talking about. A really great way to think about this is the express lane analogy. Imagine a transformer is a massive traffic jam where every car is trying to talk to every other car. It's chaos. An SSM, on the other hand, is that smooth, fast-flowing express lane that can handle incredibly long stretches of highway, or in our case, data, without ever getting bogged down.
Okay, tool number 2 is sparse attention. Now, this is designed to fix a known weakness of pure SSMs, which can sometimes struggle to connect ideas that are really far apart in a document. So instead of the transformer's super costly full attention, sparse attention is selective. It just picks and chooses only the most critical long-range connections to make.
And a good way to picture this is with the teleporter analogy. If the SSM is our express lane handling the main journey, sparse attention is like a teleporter that can instantly zap you to a crucial piece of information that's, say, 100 pages away, but only when you absolutely need it. You get all that long-range power without the constant high cost.
Now for the third piece of the puzzle, Mixture of Experts, or MOE. This is how Hydra gets the knowledge of a huge model without the slowdown. The whole idea is to build the model out of many, smaller, specialized expert networks. So for any given piece of text, you only activate the 1 or 2 experts that are best suited for that specific job. Think of it like a team of specialists at a hospital, right? You don't go and consult every single doctor for a common cold. A router, like a triage nurse, directs your problem to the right expert. This lets the model hold a massive amount of knowledge, while keeping every individual task incredibly fast and efficient. And the final tool in the kit is memory augmentation. Basically, instead of forcing the model to cram every single fact it knows into its core programming, you just give it an external memory that it can read from and write to. Yeah, you can literally think of it as giving the model an external brain. It gets a workspace for its short-term notes on the current task and a separate long-term memory to store facts. This frees up its main processor to focus on what really matters, thinking and reasoning. So we have our 4 components: the SSM Express Lane, the Sparse Attention Teleporter, the MO team of specialists, and the external brain. Now let's see how all these amazing parts actually combine to create the complete Hydra architecture. Okay, this is the core blueprint right here. Hydra is built in these blocks, and each block has 3 potential paths that data can take. Path 1, that SSM backbone, is always on. It's providing that efficient, linear processing nonstop. But then every so often, the model can choose to activate the other paths.
For instance, every third block, it might fire up the sparse attention to make those crucial long-range connections. And in other alternating blocks, it can call on its team of Mo experts to bring in specialized knowledge. And there's a little controller, kind of like a traffic cop, deciding which paths to use based on what it's reading.
Now, to really understand Hydra's efficiency, you have to look at where its size comes from. It has about 1.6 billion parameters in total, which sounds huge. But look at the biggest slice of this pie. Almost half of that total is just stored away in those inactive mixture of experts pools. These are all the specialists just waiting to be called up, contributing to the model's knowledge, but not its moment-to-moment workload.
And this right here, this is the crucial point. It's the difference between total parameters and active parameters. So while Hydra has the knowledge base of a 1.6 billion parameter model, for any single piece of text it processes, it only ever activates about 800 million of them. And that is the magic of this design. You get the wisdom of a giant, with the speed and efficiency of a model that's literally half the size.
A blueprint is one thing, but does the engine actually run? Well, the creators of Hydra ran a series of small-scale, what they called toy experiments. The goal wasn't to set new world records, but just to prove that all these different parts could work together and actually deliver on that promise of efficiency.
And this chart shows the payoff perfectly. It compares the processing speed, the throughput, of Hydra versus a transformer. You can see with short documents, the transformer keeps up just fine. But look what happens as the document gets longer. The transformer's costs just explode. That's that quadratic scaling in action. Meanwhile, Hydra's cost grows much, much more slowly, and it just pulls away, getting faster and faster in comparison.
And here's the headline number. By the time you get to a document with around 16,000 tokens, which is roughly 12,000 words, Hydra is already over 3 times faster than a transformer of a similar size. That is a massive, massive efficiency gain, and it's proof that this hybrid concept really works.
So what does this all mean? What's the big picture? Hydra isn't being pitched as the next big commercial model you're going to use tomorrow. It's being presented as something maybe even more important, a blueprint for a whole new generation of AI.
The big takeaway here is that we're moving towards a more modular future for AI. This approach gives us a path to incredible efficiency, letting us analyze gigantic legal contracts or entire books of research without breaking the bank. It lets us scale a model's knowledge just by adding more specialists, without slowing it down for every single task. The model becomes adaptable, right? It can use more power for hard problems and less for easy ones. And it allows for true specialization, where one part of the model could become a world-class expert in writing code, while another part masters poetry.
And that really brings us to the final thought. Architectures like Hydra are a huge step towards an AI that can read, remember, and reason about vast amounts of information almost instantly. So the question I want to leave you with is this: what new possibilities open up? What problems could you solve when an AI can have an entire library in its head and access any piece of it in the blink of an eye? The blueprint is here, and honestly, the potential is just immense.